Final notes in this lecture 0 file, and then move on to chapter 1 for the textbook there. So some things that occurred to me over the course of the last few years teaching this class is I had you guys use Microsoft Access, and Microsoft Access, every time you create a table within it, is going to automatically try to make the first field a primary key field, and so that little golden key appears in the design view for that first field. And usually I turn that off, not because primary keys aren't useful, but primary keys will enforce a uniqueness, and so if you do ever want to use the same value multiple times in that column, the primary key will prevent you from doing that. And so in order to let you design the tables that you want, for simplicity, I just say turn that off until you know that you want it. Having a primary key in your tables is useful for efficiency, but that we only notice that efficiency when we've got a lot of data. And so for the data that we're collecting, we don't, and actually for the data that we're collecting, I haven't given you a field in those 10 columns that I defined for you that is necessarily going to be unique between students. Eventually, you're going to be putting this data together, and you don't want your unique values to conflict with somebody else's unique values. So often, Access will just create an ID field, it'll make it auto number type, and it'll make it a primary key because it really does want to try to enforce efficiency on you from the beginning. But normally I just tell people to turn that off, because we're going to be collecting all of our data together eventually for the airfares thing, and we don't necessarily know which of our fields will be primary keys, which of them will have unique values or not. Okay, and I guess most of these notes are actually about that Access homework that I asked you to turn in. Basically create a situation where you are relating entities from two separate tables, and often that might require a third table to glue them together. Not always, but in the example that I came up with anyway, when you have mappings from many entities in one table to many entities in another table. And when I say entities, really I mean rows. But if the same actor in your actors table is going to be in multiple movies, that actor is going to have links to multiple rows in the movie table. But also, that actor is not the only actor in those movies, and so those movies will probably have multiple links back to other actors, other rows in the actors table. So for that reason, my situation ends up being described as a many-to-many linkage table design. And many-to-many designs actually need a glue table together to sort of define all of the linkages between those two entity types. But the situation that you came up with may not necessarily be many-to-many. So I just thought that I would put some examples down here, and you'll see the book will cover these examples later, so this isn't the last time that you'll ever see this. But for example, in that database design that I gave you for a university system, you have a bunch of instructors, I think. You have an instructor table, and those instructors will be teaching courses, I guess in the course of one semester is what I'm really thinking of in this situation. But in one semester, a teacher may actually teach many courses, but each one of those courses will only have one teacher. Actually, it doesn't have to be over only one semester. Probably most traditional courses will only have one teacher assigned to them. There are some courses that have multiple teachers assigned to them. We're excluding those for simplicity here. In this case, this kind of design is called a many-to-one or one-to-many design, because every individual teacher row in the teacher table will have many links going out to classes, but those classes themselves won't have multiple links going out to teachers. Those classes will only have that one teacher that they're linked to. And so either name is fine, many to one or one to many. It really depends on which table you're thinking of first. But these names come from when we were drawing representations of these tables on a whiteboard, and we're drawing the links between rows between those two tables. We just see many branches coming out of one row or the opposite. Many branches from another table coming into going into one row in the other table. Does that make sense? In that case, do I want to get into the details of this? In that case, we don't necessarily need a three-table design because let's see, I'm just going to do a quick, I guess, illustration of that over here. Let's say that we have a teacher's table and a classes table, and maybe we have a teacher named Neville who is teaching, I guess this would be name column, and class, let's call it class ID, because often we're going to have unique IDs for our classes, and maybe there's a CS 2321 course, and maybe there's a geography 100 course, and a bio 3000 course. And maybe I better put in another CS 3507 course. And maybe this is ID 1 and 2 and 3 and 4. And actually, I don't know. Maybe when I'm thinking back at the database design that I handed out to you guys, I think there was a teaches table in between. And so I think I was saying that you might only need two tables for this, but in this case, it seems like, let's just throw teaches in here. I'm definitely using a simpler design than before, than the database design I handed out. But let's say instruct ID and classes ID. This is just turning out to be the same sort of glue table design that I was thinking of before. I'm just going to add an instruct ID over here. ID, I'll call that. And so this is 01 and 02 and 03. And we've got a Professor Wolf, and we've got a Professor Hawley. Sure. All right. And so maybe Professor Wolf is teaching class number 2. I'm no longer using this. I guess Professor Wolf teaching that geography class, and Professor Hawley teaching that biology class. So same number to same number. That'll change here almost. Professor Neville teaching the CS 2321 class, and Professor Neville teaching the CS 3507 class. So this is a possible mapping between the two, and I guess I'm illustrating one to many here, and so in this case I'll just show the links between Neville and the courses Neville is teaching. And we can see that there is one record in this table that's mapping to multiple records or many records in another table. And of course, if we need the details for these courses, because here this teaches table doesn't tell me what the course numbers are. Course num, let's say. And so this links to that, this links to that. And there might also be other fields like room number. Maybe there's another field like the time slot during which that course is being taught, etc. There may be additional information in that classes table. And the reason Microsoft Access likes you to have an auto number unique ID field for all of your entities is because this one number here can represent and tie together all of the stuff from the classes table to all of the stuff that's in this teacher table here. And it does so just by storing two integers, which is just about the cheapest, most compact way of storing data in a computer. So this illustrates a one-to-many type of design here between this table and this table. And these, by the way, you'll notice that you know, each one of these courses, since there's only one instructor to one course, each of these courses only has one link to one description. This is actually a one-to-one mapping between these two tables here. And this is one way of designing your database. It's not necessarily the only way you can represent this information in your database. If you really, really wanted to design it another way, can I change this design? I might actually go back to my original idea and say, if Neville is teaching two classes, or multiple classes, then maybe Neville is going to appear multiple times in this table. In this case, I probably shouldn't call it the teacher table because this is more like some sort of teaches table, but you could end up having some sort of two-table design where Neville is teaching class 1 here and Neville is teaching class 2. The reason that we might not normally end up with a design like this is we're getting data duplicated in multiple places in this design. This is why tables get glued together. You get all of the expensive data storage, strings mostly. All of the expensive details are confined to one table that defines an entity, and then you've got all of these cheap little tables just made up of IDs, really, like the advisee and advisor table in that university database sheet that I handed out. That's an example of an intermediary, a glue table that just glues entities from two different tables together by using IDs. And so I think the three-table design that I had before would be more traditional than having a design like this where a lot of data is duplicated. Now I feel like the data table that I gave you to collect for the airfares is going to have a lot of duplicated string data, and that's fine because we're not going to have thousands and thousands of records. Our computers are going to be able to handle that. It's inefficiently stored, but the nice thing about it is that table is that database design is only one table, and so that makes it easy and convenient for us to collect our data, but it also makes it inefficient storage-wise. Yeah?
So if we had hundreds of millions of records, it probably wouldn't be a good idea to have two tables. Adding a third table could reduce a lot of that time cost when you have lots of IDs, right?
Yeah, generally, the stuff that gets duplicated in tables for efficiency is integer values, and so the ID values are what get manipulated. And then those IDs are basically indexes into tables where the expensive storage is located. So yeah, having a relational database kind of by definition is going to give you lots of tables. Just like in an object-oriented program where you decide, okay, what classes am I going to need to define? What are all the variable types that I want to invent for this program? You tend to, for a complicated program, have lots of classes. And that's why I often tie the design of tables in a database to the design of objects in a complicated program. So that's, I threw up a one-to-many illustration on the board here. If we were running a company like Amazon that was selling a whole lot of items, and Amazon also has a lot of customers who are putting these items on orders over the course of the day, some tables that we might expect to design for that situation is a customers table, an items table, and an orders table. And the orders, I think, if I were to draw that out, the orders might be the glue between customers and the items that they've ordered. It might just be two columns. It would probably be more than two columns, but something like order number, customer number, and item number would all be together in one row, and for every item that they've ordered, and maybe quantity order, I guess that's 4 columns now. And for every additional item on that order, there would be another row in that table. And so to pull up a customer's order, we're just going to pull out all of the rows from the that orders table with a given order ID, and that is how you could just store a bunch of unique orders in a table just by having each item on its own line in that in that middle table that sort of brings all that information together. And I'm not going to try to complicate that anymore. So that feels to me like a 3-table design is often going to be a many-to-many, because customers are going to tend to have many items on any single order, and multiple customers are going to have the same items on their own orders. An order isn't limited to just an item isn't just limited to one order or one customer. So that's kind of many-to-many. By default, I would think, if you happen to come up with a situation where you're listing animals as an entity in one table, and I don't know, the biological classes of animals in another table, and you're linking those entities together, this is another implementation, I would say, of many-to-one, because for every animal you have, it's only going to belong to one class, say, one category, one kingdom or phylum or whatever. However we're organizing our animals in our categories table. And so, again, if you're thinking of links between rows from one table to another in that situation, you would expect that there would be many reptiles, but there's no animal that's going to be both a reptile and a mammal, for example. So that's a many-to-one situation there. In our case, in a university, when a student has one tech ID and we don't assign the same tech ID to multiple students, that's a clear one-to-one relationship. A one-to-one relationship probably doesn't need more than one table. Often we might have one-to-one relationships between tables, but often one-to-one relationships are sort of what defines what properties each entity is going to have. One-to-one relationships tend to be columns in a table defining a particular entity. But once we get a complicated database, there could easily end up being unique connections between entities in one table and entities in another table. And these are basically the 3 patterns that we see over and over again. These are the only 3 patterns typically that define relationships in a relational database. Many-to-many, many-to-one, and one-to-one. And of course, one-to-many is the same as many-to-one. In this classroom, thinking about that situation you defined for me in that database, how many of you, thinking back on it, think that you designed a many-to-many situation? Did you have many entities in one table that were linked to multiple entities in another table? And so you had to use a glue table in between? Raise your hands if you did many-to-many.
The one.
What were your entities?
I did like football teams and then players, so that like if a player was on multiple teams, you'd have to.
You think football players are on multiple football teams?
Well, over like
maybe over time.
Yeah,
with
over
career.
There are trades that happen between teams, but in a single season anyway, probably there's only a one-to-many relationship. But yeah, if you're tracking the history of football, the history of players over time, then your database would end up being would end up having many-to-many connections. How many people, thinking back on it, had a one-to-many or many-to-one design?
That's the one.
Didn't you raise your hand for many-to-many?
I was thinking about it and I got
Yeah.
it wrong. I was like,
what
wait
were
a
your
second.
situations?
I did books and authors, and I had 2 authors going to 1 book.
Yeah. So simplifying things, maybe books only have one author, and
one author could have many books.
and one author can write many books. Now, if we're going to expand that situation to real life, where books have multiple authors, then we're going to end up in a many-to-many situation. So you were right both ways. I mean, most of the time, probably most books only have one listed author, but it's easy to find books with multiple authors in the bookstore. Michael, did you have a one-to-many, many-to-one? Because I think his degenerated to many-to-many. So I've got to find me an honest one-to-many relationship here.
I would say probably for unit quotes for games, like in RTS games, whenever you click on a unit, it gives you a voice line, or some of them give you voice lines that are unique to that unit.
Non-player characters, you mean?
Yeah.
And so you click on them and they only ever say one thing?
They say a certain thing that's specific to them.
Okay. And they don't ever say anything else?
Like for example, the Marine in StarCraft is not going to say a quote for an SCV or a siege tank. They're going to have unique voice lines specifically for them to kind of distinguish that unit.
Okay, I guess if we're talking about voice properties, that's definitely going to be a one-to-many. If that character says multiple lines, then the relationship between characters and lines will be many-to-many. But yeah, we can craft a one-to-many sort of relationship out of that situation. Anybody have a one-to-one relationship between your entities in the table? That would be a little bit odd. Probably those wouldn't occur to you by default within that assignment description. But okay, I just thought I should check on that. But we're going to see some examples of that, not only in your university database schema, but in other situations that I throw up here on the board. Let me move just for a moment over to the airfares assignment. Again, it's occurred to me that probably you shouldn't be collecting primary keys, or you probably shouldn't have auto number fields in your design. I didn't leave room for that in the schema that I gave you, unless you're putting those values in that last comment field that I left unassigned for that sort of thing. But I already talked about if one of your flights is canceled, you can choose another flight and then just track that one forever afterwards, just so you're not suddenly collecting less data than you used to be. If I were you, probably right now, I suspect that most of you are collecting your airfare data all in one file in an Excel sheet. Are you? Because collecting your data in an Excel sheet is probably much easier than creating a database table and having to open that every time that you're collecting data. Plus, you can save an Excel sheet on a thumb drive and have that with you whenever you're collecting your data. It's much more compact than having an access file, and then you're relying on whatever machine you're using to also have access on it. I would suggest that you collect your separate airfare, your separate air routes in separate sheets, just because it allows you to copy data down more easily than if all the data is in one And is there another reason why? Not really, because when we do collect all of our data together, you're probably going to want to take the contents of all three of those sheets, put it into one sheet, and that's what you're going to export as a CSV, which will be imported into the database. So, I mean, I don't know. If you want to collect everything in a single Excel sheet, I suppose that's fine too. I don't see any immediate problem with that, except for all that duplicate data, because airlines and flight numbers and things are basically going to be duplicated data for every single row that you pull in. If you don't want to have to type that in every single time, I suppose you could copy-paste the 3 rows from your last collection. That would work. I talked about when you're making graphs of your airfares that the x-axis should be in date-time format. And the reason that I like that, the reason that I like that you're saving your data into an Excel file is because you can define a column to contain date fields or time values. And if Excel understands your data as date values and time values, then it will easily import into Access that way. If Excel doesn't represent your data correctly, then those rows are likely to be rejected in the import process when you try to bring them into Access. So there is one benefit to sticking with Microsoft products is they should be able to communicate with each other more easily. Again, any questions on the homeworks turned in on Friday? Any other questions on the ongoing airfares project? You should continue collecting your airfares. We're going to do that every day from now until the end of October. And so when I get around to grading the 7 days of airfares that you turned in for me on Friday, if the reason I had you turn it in after 7 days is I want to catch errors early. Like some people were collecting over the wrong departure return range. Some people weren't collecting the dates and the times. And we need everybody to be collecting exactly the same kind of information and the same 10 columns of information, or 9 in our case if we're not using the comment field. Oh, there it is. Any questions on the data design that I'm having you collect? You're not thrown by the fact that I'm asking your what is these are airport codes. And again, why is my because it's not on. There it is. Flight numbers. Why are my flight numbers non-numeric? Isn't that field name flight number? That doesn't bother you guys? That it's a string and not an integer? I mean, it wouldn't make sense to make it a float, I guess. Yeah.
Some airlines have different numbering schemes. Some
Yep.
of them only go up to like 3 digits. Some of them go up to like 6, 7 digits. Some of them have like.
Some of them have letters? Well, it's a good thing we made that a string then. Yeah, I think that the reason I made that a string is because I suspected that there might be a United Flight 328B or something like that. And so if something like that happens, we can't make the data type integer as much as we'd like to. No problems with this? Data collection is proceeding apace? No problems? All right. And by the next time we meet on Wednesday, you should have grades and feedback on your 7-day assignments. All right, I think that's the last thing that I wanted to talk about in there, so I'm going to move that aside and start moving forward on the book. And this is chapter 1. This is mostly just going to be table setting. A lot of obvious stuff. Okay. So if we're going to define a database, we know that a database is a collection of related data. We are collecting data data on things that it should make sense to us. Which bits of data should go together? That allows us to decide, okay, that this data should go in this table, and maybe I need another table to store data about these things. And of course, most of the time when we are using a database, when we know that we're using a database, it's because we're actually using some database application on a computer system. But that doesn't mean that just computers are databases. Before Microsoft Access existed, before computers existed, people were still saving data. How were they saving data? On typewritten sheets, text files are databases. Every row in a text file is, a row that can be read in by your Python program, and maybe the data on every line of that file is the same number of integers separated by commas. And so we can implement a database table as a text file. In fact, that's kind of what CSV files are. It is between each value and each column on each row of your Excel sheet or your Access table, you have all of the data values that are stored in those columns. So what a database is generally created for is to represent some sort of mini universe, which is called a universe of discourse. That is, this database that I'm having you guys collect, it's basically tracking the world of airfares, and so we'll have a certain number of flight numbers and 3 destinations, and the fares between cities for all of these different companies that are serving that particular route. That's going to be our universe of discourse. This is going to be a super simple database. It's going to be in one table, and one table databases, they might as well be a text file. Ours will be, once we put everybody's data together, one very, 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 very long text file. But it should have 10 columns of data and the same data, the same data types in each column, if everything works and it goes smoothly. So okay, our mini world is supposed to represent some aspect of the real world, and the data should be logically coherent. It should hang together. So if it doesn't hang together, then our database actually won't be representing the part of the world, the mini world that we're trying to represent. That university database design that I handed out to you was put together thoughtfully in such a way that this table represents students, this table represents instructors, this table represents courses, this table represents buildings, this table represents time slots. And so within the time slot table, all of the column names, all of the properties have something to do with time slots. All of the stuff in the student table, all that data is related to each other because we're putting student name together with student ID, together with other student-related things. And then if we want to, we've got all of the instructor data in the instructor table. And if we want to collect data from 2 separate tables like that to have any special sort of meaning, the example I always go back to is the advisor table. Then we create links between those tables. There's an advisor table between the instructor table and the student table that puts instructor ID together with student ID, and those rows represent which faculty members are advisors to which students. And is that a one-to-one relationship? It is if it isn't. Because usually faculty will advise multiple students, and maybe we might simplify things and say every student only has one advisor. But here at BSU, I think that every student has like 3 advisors, right? A general advisor, a major advisor, and then there's an advisor for some reason I think that you guys have 3 advisors. If we were to represent that in our system, that would be a many-to-many grouping, linking of instructor entities with student entities, assuming that all of the advisors are instructors. I guess the design that I handed out wouldn't fit that very well because I think 2 of the 3 advisors are not instructors. They're in the trio office or whatever those other offices are in the administration building. Deputy? But anyway, whenever we design a database, it is built for a specific purpose to represent a certain aspect of the world whose data we need to track over time maybe, or whose data, whose combination will be useful to us somehow. This university wouldn't be able to run if it didn't have its own design, its own database design, which is, probably somewhat similar to that university design that I handed out as an example, but I bet my example is super simplified compared to what BSU is actually using. They're probably also not storing all that data in an Access database, because Access really doesn't work very well for multiple people at once. And every administrative assistant, every secretary, every person in the deputy building needs to access the tables in BSU's database in order to get their jobs done, in order to make sure that students end up in the right classes, are being charged the right amount of tuition, and ensure that business goes along smoothly over the course of the semester. So we can have databases represent things like in the banking industry, the transactions. You would be very disappointed if you visited if you viewed your account 2 days in a row and you didn't take out any money from the ATMs from that account, and the amount changed. So databases are tracking how much money is in your account, how much money gets added with every new paycheck, and then after every withdrawal, how much money is left in your account. Of course, the websites that you guys are consulting for these airfares you wouldn't be able to look these things up on the internet if there wasn't some database that was you were pulling these airfares from, that you were finding the schedules between cities for. Of course, universities need to track your grades in order to give you your transcripts when you request them when you're applying for jobs or graduate schools or different programs. Stores are managing their sales, they're tracking their customers, they're making sure they know what products they have in store and what products that they need to order, and figuring out which products have been purchased by customers so that they know what's popular or not, and what to reorder quickly, and what to order in smaller quantities if necessary, so it doesn't take up too much space while it's being while customers are depleting the supply. Most stores don't have a whole lot of back of store space. Walmart, Lucan's, they have some storage space in back, but they don't want to use it to store stuff that doesn't sell. Most of their stuff, they want it to be on the shelves. Once it's out on the shelves, you ask somebody, hey, do you have any of this in back? A lot of the time they say no. They just don't have the room in back to store all of the stuff that they have out on the shelves. Online retailers, Amazon, those are basically just database companies. They keep track of all the orders you've ever made through them over the last 10, 20 years. They use the items that you placed on past orders in order to make suggestions to you. If you like this thing, here's a link you can click on to reorder it automatically every month. Or you might like these other things because they're similar to this thing which we don't sell anymore. Again, just about every industry is going to have some database tracking their information in order to make that industry run smoothly. You're not going to get paid by whichever human resources industry employs you if they don't know what your social security ID is, and they don't know how much you get paid every month, and if they don't know what your bank account number is. And so all of these things go into databases in order for life as we know it to go on. Databases touch every single aspect of our lives, whether we know it or not. So often, when we talk about database systems, we might call it a database management system, because really it is a piece of software that is written in order to manage data, to store it in such a way that it can be retrieved quickly, because often we're going to be asking questions of the database management system and say, return all grades associated with Tyler Hushagen so that I can order them by date and return them as a transcript, for example. And so as a piece of software, a database management system doesn't necessarily just do one thing. It's basically a whole bunch of different programs that are tied together behind one graphical user interface. And so you click on buttons to execute various functions. And you'd be unhappy if you clicked on the Create Table button and your application spun and spun and spun and made you wait more than 4 or 5 seconds before it shows you the interface that allows you to build that table. It needs to be efficient. When you ask it a question, you expect that the answers come back to you in table format quickly. It needs speed is important, but also I guess the design of the graphical user interface or the design of the output that it shows you should be understandable and convenient as well as efficient. Otherwise, you're not going to use that company's database product. And any database management system, in order to be called a database management system, should allow you to define a basic structure for your tables and then actually save that data onto the hard drive such that the data that needs to be, often the data in one column is strongly associated with data in another column, and so often that data is stored next to each other on the hard drive as well. So when you collect one, you collect the other one. I guess nowadays, if we're using those, I'm still thinking of hard drives that are spinning disks, but if we're using solid state systems, then data doesn't necessarily need to be next to each other in order to be retrieved efficiently. But again, the idea of efficiency underlies everything that we do when we're writing these database management system programs. And we're going to need to connect data together, to link data together, to manipulate data, to combine data together. And so that also has to be efficient. And of course, being able to export data, import data, share the values that are stored within the data structures that you wrote in order to be able to do these various things, to be able to ask particular questions that only returns Tyler's data or Sam's data in order to accomplish whatever task you're responsible for accomplishing today. Views are a particular type of view. Views are associated with tables or queries, but you might notice that when you're looking at your, I guess one example is your DARS report. I think you often see stuff on your DARS report, and then you go talk to your advisor, and your advisor sees more stuff than you do. And so views are basically things that filter out values from the database table, and so things that students aren't supposed to see, like teacher salaries, aren't going to be visible in student views, but maybe teachers will see those things as well as other things that students can't see. And maybe things that are private to students aren't shown through the teacher view. So we mostly talk in this class about tables and then the questions that we ask of the data in those tables. And a view is basically something that either shows you a table or the result of a query, which is basically a custom table itself, and shows you a filtered view of all the stuff that you're allowed to see from that data set. I don't think we ever actually implement any views in this class, but they do get mentioned every now and again. So a database system is just a collection of application programs that are tied together behind some graphical user interface accessed by the users or the programmers of that database. And then when various functionalities are chosen from that GUI, then they call the actual software that goes in and collects the data from wherever they're stored on the storage devices and puts it together in such a way that it answers whatever questions were asked to them. Often when a database is represented to us, they show us actually two sort of hard drive icons. One hard drive is where all of your actual data is stored. That's that stored database icon there. But there's often a metadata hard drive too, and this basically stores what you see and access when you're looking at the design view of a table. Mostly a table, not necessarily a query, but metadata is basically what are the names of the fields and what are their types. that create the objects in this table, and the most important objects defined in a database are, of course, the tables that are organizing the data for particular entities. And of course, this is a vast oversimplification, but I pulled that from your book here. I was talking about how before computers existed, basically data was stored on text files. So you can imagine the data that you're saving in your Excel file for these airfares, you're just typing those onto a text file, onto a sheet of paper with a typewriter. You see any downsides to that sort of manner of recording information?
Can't combine them.
It's not easy. Come on, you can get out a scissors and cut out those rows. Yeah, no, they are very hard to combine, and when you are combining them, how are you going to do it? You're going to match a row on this sheet of paper with this sheet of paper, and then you're probably going to copy it onto a separate sheet of paper by hand or typewriter. And so, yeah, data processing was very much slower before digital databases existed like that. Plus, I'm going to great lengths to make sure that the data you guys collect is compatible with each other. Data in different rooms was not compatible with each other in your given office. Everybody stores data in their own way for their own office. I mean, maybe people in different rooms store data in the same way just so it can be compatible to each other. But you go from one building to another building, and you can't necessarily put that data together because, again, even here, people are wanting to create extra columns for that 10-column design. Just due to what different people think are important, if I didn't put those strictures on you, everybody in this classroom would have, some people would have a 5-column table, other people might have a 12-column table, and nobody's tables would be easily combinable that way. So different offices will track data. Will track data in different ways. They'll basically create different objects, different table designs, and so just that means that different offices, data that's in one table for one office might actually be scattered among multiple tables the way another office tracks it. So yeah, So drawbacks that still plague us are data redundancy, but if you are compiling data by hand and collecting multiple rows of data like that, it's easy to end up with a silly design like I have on the board here, where I have Neville appear multiple times in the same table just because I want to track that Neville is teaching multiple classes. So data redundancy happens easily. If you're typing stuff in by hand, you're misspelling things, and so now you've got data values which a human knows that this value is the same as that value, even though the characters are different, it's misspelled in one or the other, but a computer is not going to be able to handle that. We still have people inputting data by hand, and people are still mistyping things, and this is how errors happen in real-life databases when a computer expects values to be the same in different tables if that data needs to be connected to each other. This is actually another good reason why Access likes you to have complicated string data represented by a single number, because it's easier to type in an integer without making a mistake than reduplicating a whole big long line of text necessarily. So that's something that saves us. Let's see, and of course difficulty in accessing data, putting it together. And if you did want to combine multiple offices' data together, then you would have to come up with a different process for every project that required data from different offices to be put together. So it is, having these digital database applications has enormously sped up and simplified the process of cooperating and being able to use each other's data, as long as some thought has gone into the design of making everybody's data compatible. Again, that's the importance of choosing good data types and representing stuff in ways that make sense to other people. All right, I think that's enough for today. Thank you for your attention. I will continue with this on Wednesday, and then start moving into the fun stuff on Friday.